Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
An inquiry into the foundational claims of Paul Dirac's 1997 paper on the quantum theory of radiation. The intellectual landscape of 1997 was one of profound conceptual upheaval and brilliant, partial successes. The new quantum mechanics of Heisenberg, Born, Jordan, and Schrödinger had provided a powerful mathematical framework for describing the behavior of atomic systems, yet a deep and perplexing chasm remained: the interaction of matter with light. The very process that made the quantum world observable was treated with a hybrid, philosophically unsatisfying approach. Atomic systems were quantized, obeying the strange new rules of probability amplitudes and discrete energy states, while the electromagnetic field was still a continuous, classical entity described by Maxwell. Paul Dirac, in his paper The Quantum Theory of the Emission and Absorption of Radiation, addressed this fundamental inconsistency with a work of extraordinary depth and economy. This essay provides a meticulous, section-by-section evaluation of the internal claims, mechanisms, and arguments presented within that foundational 1927 publication, charting the logical progression that established the bedrock of quantum electrodynamics. We will examine the specific assertions Dirac makes, the mathematical machinery he deploys, and the evidentiary power of the results he derives, thereby illuminating the precise architecture of this monumental contribution to physics. Section 1. The problem of interaction and the call for a symmetrical theory. Dirac commences his argument by identifying the central deficiency in the contemporary understanding of radiation phenomena. The prevailing semi-classical methods, which coupled a quantized atom to a classical electromagnetic field, could offer explanations for absorption and stimulated emission. These processes could be pictured as an external classical wave perturbing the atom and inducing transitions. Spontaneous emission, however, remained an enigma. Within a purely classical framework, an excited atom would radiate, but in quantum mechanics, an atom in a stationary energy state is, by definition, stable. There was no inherent mechanism within the existing Schrödinger theory to compel a spontaneous transition to a lower state accompanied by the emission of light. Einstein's phenomenological introduction of a probability coefficient, the famous coefficient, was an accurate description of observation but lacked a derivation from first principles. Dirac's opening claim is that a satisfactory theory requires placing matter and the electromagnetic field on an equal footing. Both must be subject to quantum laws. This initial assertion frames the entire paper as a quest for a symmetrical, unified quantum description. He posits that the interaction between the atom and the field is the key, and a full quantum treatment of this interaction will yield the known laws of emission and absorption as natural consequences of a single, coherent formalism. The core argument of this introductory section is one of philosophical and physical necessity. The inconsistencies of the hybrid model demand a new, fully quantum approach where the radiation field itself possesses quantum properties. Section 2. Quantization of the radiation field. This section contains the paper's most radical and consequential conceptual leap. Here, Dirac presents the mechanism for quantizing the electromagnetic field. He begins with the classical description of a radiation field in empty space, described by a vector potential. Following a standard procedure, he decomposes this vector potential into a Fourier series, representing the field as a superposition of monochromatic plane waves, each characterized by a specific frequency, polarization, and direction of propagation. The energy of this classical field, its Hamiltonian, is then an integral over all space which can be expressed as a sum over these individual modes. The pivotal claim is that this system is dynamically equivalent to an infinite assembly of independent harmonic oscillators, with each oscillator corresponding to a single mode of the radiation field. Having established this analogy, Dirac applies the rules of quantum mechanics. He promotes the amplitudes and phases of the Fourier components, quantities that were previously classical variables into quantum mechanical operators. These operators, like the position and momentum operators for a simple harmonic oscillator, obey specific commutation relations. The Hamiltonian of the radiation field thus becomes a sum of quantum harmonic oscillator Hamiltonians. This procedure has immediate and profound consequences. The energy of each oscillator, and therefore each mode of the radiation field, is quantized. The allowed energy levels are given by the quantity n+1/2, all multiplied by the reduced Planck constant times the angular frequency. Where n is an integer, Dirac interprets this integer n as the number of photons present in that specific mode. The formalism, therefore, yields the corpuscular nature of light directly from a field quantization procedure. The operators he constructs are what we now recognize as creation and annihilation operators. One operator, when acting on a state, increases the occupation number n by 1, corresponding to the creation of a photon in that mode. Its adjoint operator decreases n by 1, corresponding to the annihilation of a photon. The state of the entire radiation field is specified by providing the set of all occupation numbers, one for each mode. This section's central achievement is the construction of a mathematically rigorous and conceptually complete framework for a quantum field, one that inherently contains the particle nature of light. Section 3. The combined system and the interaction Hamiltonian with the atom and the field both described by quantum Hamiltonians. Dirac proceeds to construct the Hamiltonian for the total interacting system. He posits that the total Hamiltonian is the sum of three terms: the Hamiltonian for the atom alone, the Hamiltonian for the radiation field alone, and a crucial third term representing the interaction between them. The claim here is that the entire complex phenomenology of light-matter interaction can be captured by a specific, well-defined interaction term for a single electron in an atom. He derives this interaction Hamiltonian from the principles of classical electrodynamics, replacing classical quantities with their newly minted quantum operative equivalents. The resulting interaction term is proportional to the product of the electron's momentum operator and the vector potential operator of the radiation field, evaluated at the position of the electron. This form of coupling is critically important. The vector potential operator is a linear combination of the creation and annihilation operators for all field modes. The interaction Hamiltonian therefore contains terms that connect a state of the atom with a state of the field. Specifically, it has matrix elements that connect an initial state of the system, comprising the atom in one energy level and the field with a certain number of photons, to a final state where the atom is in a different energy level and the number of photons in one of the field modes has changed by exactly 1. An atomic transition downwards is coupled to the creation of a photon, while a transition upwards is coupled to the annihilation of a photon. The argument presented is one of elegant encapsulation. This single, compact interaction term provides the dynamical mechanism for all forms of emission and absorption, unifying these seemingly distinct physical processes under one theoretical roof. Section 4. Application of time-dependent perturbation theory. Having established the total Hamiltonian, Dirac confronts the problem of calculating the consequences of the interaction term. The interaction Hamiltonian is assumed to be small compared to the Hamiltonians of the atom and field separately. This justifies the use of perturbation theory. Specifically, he employs the method of variation of constants, a formulation of time-dependent perturbation theory he himself had recently developed. The central claim of this section is methodological, that this perturbative approach is sufficient to calculate the rates of transitions between the states of the combined system. He considers a system that starts at an initial time in a specific eigenstate of the unperturbed Hamiltonian, for example, the atom in an excited state and the field in the vacuum state. The interaction term then causes the system to evolve into a superposition of other eigenstates. Dirac calculates the probability amplitude for finding the system in any other particular state at a later time. He shows that for short times, the probability of having transitioned to a new state grows quadratically with time. The rate of this growth, The transition probability per unit time is proportional to the square of the magnitude of the matrix element of the interaction Hamiltonian connecting the initial and final states. This result, now a cornerstone of quantum mechanics, is applied here with tremendous effect. The validity of the framework hinges on the assertion that this calculation accurately reflects the physical processes of emission and absorption. The evidence for this assertion will come from the results it produces in the subsequent sections. Section 5, the derivation of spontaneous emission. This section presents the first major triumph of the theory and provides powerful evidence for Dirac's claims. He applies the formalism developed in the preceding sections to the problem of spontaneous emission. He considers an atom initially in an excited state, with a radiation field containing 0 photons in all modes, a vacuum state. In the semi-classical theory, this system is stable. In Dirac's theory, the interaction Hamiltonian still possesses non-zero matrix elements connecting this initial state to a final state, where the atom is in a lower energy level and the field contains 1 photon with the corresponding energy. The term in the vector potential operator responsible for this is the creation operator. The astonishing result is that a transition is predicted to occur even from the vacuum field. The physical interpretation, a profound insight, is that the zero-point energy of the quantized field, the 1/2 times the reduced Planck constant times the angular frequency, term in the Hamiltonian, provides the quantum fluctuations that effectively stimulate the atom to emit. The vacuum is a dynamic entity. Dirac proceeds with the calculation of the transition probability per unit time. He sums over all possible final states for the emitted photon, meaning all directions and polarizations, consistent with energy conservation. The result of this calculation is an expression for the rate of spontaneous emission. When he substitutes the relevant physical constants, this expression is shown to be identical to Einstein's coefficient. This is a monumental achievement. A purely phenomenological law, which for 2 decades had stood as a postulate, is here derived from the fundamental principles of quantum mechanics. This successful derivation provides the strongest possible validation for the paper's core premise, the necessity of field quantization. Section 6. The derivation of absorption and stimulated emission. Following the success with spontaneous emission, Dirac turns his attention to the other 2 processes described by Einstein, absorption and stimulated emission. He considers an initial state where the atom is in its lower state and the radiation field is bathed in incident light of the appropriate frequency, meaning the occupation number n for the corresponding field mode is greater than 0. The interaction Hamiltonian's annihilation operator term provides a mechanism for a transition to a higher atomic state where the final state of the field has n-1 photons. The calculated transition probability for this absorption process is proportional to n, the number of incident photons, which is directly proportional to the intensity of the incident radiation. This result matches the known behavior of absorption. He then analyzes stimulated emission. The initial state consists of the atom in its excited state and a field with n incident photons. The creation operator term in the interaction Hamiltonian provides the mechanism for a transition to a lower atomic state, resulting in a final field state with n+1 photons. The crucial result of the calculation is that the probability for this stimulated emission process is proportional to the quantity n+1. The term proportional to n represents the stimulated part of the emission, driven by the incident radiation. The term proportional to 1 is independent of the incident radiation. It is precisely the spontaneous emission term calculated in the previous section. Dirac's formalism thus elegantly combines spontaneous and stimulated emission into a single process. He demonstrates that the calculated rates for absorption and stimulated emission correspond exactly to Einstein's B coefficient and, crucially, that the theory automatically produces the correct thermodynamic relationship between the A and B coefficients. This unification of all 3 radiation processes within a single coherent mathematical structure serves as definitive proof of the internal consistency and predictive power of his quantum field theory, Section 7 General Theory and Relation to Dispersion. In his concluding section, Dirac reflects on the scope and implications of his results. He argues that the theory provides a more complete foundation for understanding phenomena like resonance, radiation, and dispersion. The contemporary theory of dispersion, developed by Kramers and Heisenberg, was based on a virtual orchestra of oscillators corresponding to possible atomic transitions. Dirac's theory provides a concrete physical reality for this picture. The interaction of light with an atom involves intermediate, or virtual, states where a photon is absorbed and then re-emitted, or vice versa. His perturbation theory framework is capable, in principle, of describing these higher-order processes that give rise to the scattering of light. He thus claims that his work provides a deeper justification for the successful dispersion formulae. He also exhibits remarkable scientific candor by acknowledging the limitations of his work. The entire treatment is non-relativistic with respect to the electron. The calculation uses a simplified model of the atom and the interaction. He is aware that a complete theory would require a relativistic description of the electron, a challenge he himself would famously meet in the following year. This final section demonstrates a keen awareness of the theory's place in the broader research program of physics. It successfully solves the immediate problem of emission and absorption, while simultaneously pointing the way toward future investigations into scattering and relativistic quantum mechanics. His claims are powerful but carefully bounded, a hallmark of his scientific style. Conclusion: a 1927 paper by Paul Dirac on the quantum theory of radiation stands as a work of profound and lasting significance, because the claims it makes are so thoroughly and successfully substantiated by the logical and mathematical structure it presents. Its central assertion that the electromagnetic field must be quantized to achieve a consistent theory of its interaction with matter is vindicated by its spectacular success. By treating the field as an assembly of quantum harmonic oscillators, Dirac constructed a framework that yielded the existence of photons as a natural consequence. The elegance of his interaction, Hamiltonian, provided a unified mechanism for what were previously considered three distinct processes: spontaneous emission, stimulated emission, and absorption. The derivation of Einstein's and B coefficients from these first principles provided irrefutable evidence for the validity of his approach, transforming phenomenology into derived physical law. The paper did more than solve a problem, it established a new paradigm. The method of second quantization, the application of quantum rules to a field, became a foundational tool of modern physics, extending far beyond electrodynamics into the study of all fundamental forces. While the theory presented was a first step, a non-relativistic one at that, its core conceptual architecture, the very claims about how a quantum field behaves and interacts, proved to be enduring. It was the birth of quantum electrodynamics, a theory whose foundational logic, as laid out with such clarity and intellectual force in this 1927 masterpiece, continues to underpin our understanding of the universe.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.